not solid wheels like gears. Pulleys have recesses to reduce weight and manufacturing costs. As a result, belt drives are generally lighter than conventional gearboxes. But belt drives also have disadvantages. Depending on the environmental conditions, belts age to a greater or lesser extent, which means that they lose their elastic properties over time and need to be replaced. For this reason, belts can only be used within a certain temperature range. In addition, the belts will plastically stretch over time, which means that they need to be retensioned at regular intervals. Another disadvantage of some types of belt, such as flat or V-belts, is the aforementioned elastic slip, which leads not only to a loss of power, but also to a loss of speed. Such belts are therefore not suitable for precise positioning. Slippage can only be avoided with timing belts due to their positively locking power transmission. Belt drives usually take up more space than conventional gearboxes, which can be a disadvantage in some cases. This is due to the fact that the pulleys cannot.
I don't think that's often the case. I mean, space requirement, I mean, you already have the drive there anyway, you know.
Not be placed directly next to each other, whereas in conventional gearboxes, the gears actually mesh with each other and can therefore be arranged in a more space-saving manner. In addition, as the center distance decreases, the wrap angle decreases and can become unacceptably small. This can be compensated for by the use of idler pulleys, but this not only increases the design effort, but can also increase the space requirement. When using idler pulleys, it should be noted that the belt is also bent around the idler pulley during rotation. This increases the so-called bending frequency and can lead to premature fatigue of the belt. Another disadvantage of belt drives compared to conventional gearboxes is the relatively high bearing forces due to the need to pre-tension the belts. Pretensioning the belt often requires increased design effort.
Okay, that's a good summary of it. What he mentioned about the fatigue is a situation where you have a really big wrap angle. Like you go round and around. You know, if your wrap angle is that much, you're basically bending the belt this way, and then bending the belt this way, and this way, and this way, right? And that's fatigue. So it can increase fatigue, and that's why your car belts cracks a lot after some time. All right, so with this, let's go into the calculation, but this is probably a good place for a break. Okay, so take like 10 to 15.
It's yours. Mom and dad. One I get another one. No, it's not gonna kill your laptop. But because of constant overheating, it's a game. It's a game. It's also really using laptop. Tapi kan ini di background video bukan kayak ini kan laptop juga yang mungkin baru kali bikin ya. How fast? Ya karena dia admin gimana mau PC? Oh mau bawa PC kerapnya pas ya ini yang harus GP di atas ini kalau bukan iya kayak sombong emang iya jadi juga iya oh mau tinggal di sini GP harus di atas BOD kalau sama security aja ya security iya oh tapi cari lihat posisi juga ya kira-kira posisi gitu aman atau banyak linking kapasitas negatif lagi saya pikir apa dua kan tapi Satu lagi mau di, satu lagi mau di. Agaknya lebih ayam.
By the way, have I covered the questions in the pre and post test? The pre-test.
The clock wheel.
Oh, the clock bell. Yeah, I forgot to discuss that.
This program will focus on
I forgot to play one video. We'll play it after. Is it just me or is it blurry? Is it out of focus? Okay.
No, you can see here. Oh, potong gua aja. Lu nggak usah kirim, tapi potong dari print gua. Coba bisa nggak sih barang belum pernah bawa rock bike itu rock bike tuh ini. Iya. Nah, 330 kan. Kita tuh wah. Seribu biaya ininya, biaya aplikasi. Dapat berapa? Kalau lo bayar nih, itu belum gua. Sebelum seribunya nanti COD aja.
Okay, everybody's back. I want to run some of these videos that I forgot. I have.
This program will focus on a small but crucial component of the power belt. V-belts are simply transmitters that effectively link a power drive to a needed function.
By the way, V-belts can also be run multiple belts. I mentioned the serpentine belt is a V-belt but rift, right? Like that. Now, industrial V-belts are one pieces at a time, like that. Okay? It's shaped like a V, but it's thick. And the bigger V-belts will have a bigger trapezoidal cross-section. Okay? But these V-belts can be run in parallel, like that, side by side. And so your pulley is basically multiple belts pulley also.
The belts are easy to select, simple to install, and offer years of reliable performance. The first V-belts appeared in the structured belt fits into the wedged groove of the shift.
Now, another type of belt is called a Koch belt. It's basically a V-belt. So the cross-section is still a V-belt, but on the inside, there is some cutouts. Okay? Now, Koch belt will be shaped like that. It's different than a timing belt where you got some flat spots here. Okay? A timing belt will have these flat spots. But a V-belt, a Koch belt is basically small cutouts is to reduce the stresses when you wrap around small angles.
To create a matched fit. When the drive is activated, the pulling power comes from the action of applied tension, which forces the belt to wedge tightly into the shiv groove. By using the wedge principle, the V-belt gains the advantage of tremendous gripping power. Besides this power advantage, the V-belt offers many other advantages for they are made of natural and synthetic fibers and rubber, but they still...
The V-belts, if you cut it, there are metal wires inside. So these are metal, the rest is rubber. And the rubber provides the flexibility part, the metal provides the strength.
Utilize the original wedge concept to harness power. The wedge-shaped belt fits into the wedged groove of the shiv to create a matched fit.
So the pulley itself has a wedge like that. Okay? So this is the cross section of the pulley, and here is the V-belt. Okay? So it fits, and it's kind of self-wedging. The more torque you create, the more it pulls and the more it sits into the wedge. So it's a nice self-tightening or self-gripping design.
When the drive is activated, the pulling power comes from the action of applied tension, which forces the belt to wedge tightly into the shiv groove.
So it's kind of a self-gripping.
By using the wedge principle,
So this is a multiple V-belt arrangement, okay? Side by side. So the pulley itself has multiple wedges.
a V-belt gains the advantage of tremendous gripping power. Besides this power advantage, the V-belt offers many other advantages for industry in its efforts to reduce equipment repairs and minimize downtime. Operation demands efficiency and minimal maintenance. The V-belt drive is the logical choice. Unlike roller chain, V-belts require no lubrication. They device equipment. Finally, V-belts are so effective that even when proper installation and maintenance procedures are neglected, the belts will operate with some degree of success. A V-belt is designed around two concepts, strength and flexibility. The strength is provided by a row of tensile cords. The cords serve as the load-carrying component and are made of twisted synthetic fiber. The compression section is made of synthetic rubber. It supports the tensile cords evenly and compresses while bending around the shifts. Conversely, the tension section, located above the cords, is designed to stretch as the belt bends around the shifts. The cover or top fabric is made of a rubberized fabric designed to provide wear resistance and increase belt flexibility. In more recent years, belts with a cog construction have become popular for specific applications. The cogs offer greater flexibility, and with proper usage, it is possible to get up to 25 to 50% more belt life than a standard V-belt. The cogs make it possible to use smaller diameter pulleys, resulting in more compact drives. Additionally, standard V-belts generally have an ambient temperature limit of 140 degrees Fahrenheit.
Okay, I think that covers it. There's a unique type of belt called a CVT belt, but I think we can skip that one. I mean, that doesn't count as belts in the traditional sense that we are discussing it. So I think I've covered most of the question on the post-test. Yeah? Okay, or all. I want to move forward to the design of belts. Okay, now we are going to use an industrial catalog from Bendo, B-A-N-D-O, and I attached the. Why don't you open the PDF if you have a laptop with you? Open the Bendo Design Catalog PDF. I want you to be familiar with that because we're going to use that for the exercises for belts. Okay? Now, the design catalog itself has a procedure of designing, but I kind of modified a bit in ways that I think makes more sense. So we're going to go through these steps if you're given a design class, and I'll just explain it as we go, as usual, rather than going through the steps theoretically. Okay? So first, this is an example. A customer needs a V-belt drive for an agitator. Agitator means mixer. Okay? That is in operation continuously, so you kind of basically runs all the time. The driving motor is 5 horsepower, rotating at 900 RPM. The outer datum diameter is 3.0 inch. We're working with inch. It's an American catalog. So datum simply means the point of contact at the belt. So basically the diameter, okay? The effective diameter. And then you have the driven sheave. Sheave means pulley, okay? Rotates at 250. So it's a speed reduction, as usual, okay? Speed reduction with a certain ratio, and we have the center to center distance at 32 inches. Okay, so let's draw up what we have. We have a smaller pulley and a big pulley. Which one rotates faster? Smaller pulley rotates faster. Okay? So this is 900 RPM and this is 250 RPM. Okay? So that's the belt. The center to center distance is 32 inches. We have 5 horsepower motor at 900 RPM, 250 RPM. This is 3 inches. The big D, I'm going to call it big capital D. And this is the small diameter D. We are not given, and we are about to select the setup. So we're going to have to select the belt. We're going to have to select the small pulley as well. The first step is to calculate the speed ratio. And this determines our smaller pulley selection, right? So the speed ratio is 900 divided by 250. So we have a 3.6 to 1 ratio. Okay? So we're going to have to select a smaller pulley diameter that will, sorry, this is not, that's not the big diameter. The driving motor diameter. So this is the driving motor diameter. Okay, so the given one is the small pulley. Second, we have the calculate the design requirement. Design horsepower requirement. And we have 5 multiplied by what is called the surface factor. By now, you're probably familiar with these terms. You always multiply by something to make it worse, right? And so the surface factor is pretty much the situation of the application, which then determines how much do you want to make it worse. So we have an agitator for liquids. This is a lookup table in the PDF. Okay? And we're operating continuously, meaning 16 to 24 hours daily. the surface factor is 1.2. So we multiply that by 1.2. So we essentially need 6 horsepower. Okay? Now, step 3. We're going to select the belt family based on the design horsepower. Okay? The family of belts in the catalog falls into a mapping. If you look at the bigger chart, there is a 3V, 5V, and I think an 8V. Right? The way you look at the chart is you first take a look at the x-axis where you have design horsepower, and the vertical axis is the RPM of the faster shaft. Which one is the faster shaft? Smaller one. Trying to brainwash you here, okay? Smaller pulley, faster RPM. So 906 horsepower because multiplied by the surface factor is 6. The intersection falls into this area, which is the 3V or the 3VX belt family. So it's basically the cross section. Okay? So 3V is small, 5V, and 8V. Okay? So 3V. It's simply bigger. And as you can see, the boundaries, this line here, says that faster RPM, actually, for the same horsepower, for faster RPM, you actually want to go smaller. Does that make sense, you think? Yeah? Smaller, faster. Smaller kind of goes with faster. So you want a smaller cross-section for faster RPM. And that's why you see this line. This is not a strict line. I mean, again, there are multiple answers in engineering design. There is no, it's not like 4 plus 3 equals 7. Okay, that's analysis. So in design guides, yeah, you have this line, but what if you fall right at the line? Well, it's really up to you. And in many ways, it's situational. Okay, so, you know, it's not a solid line, it's a kind of a general guide. But we clearly fall here in the 3V area. So for step 3, we're going to select belt family from 3V. And we're going to select the pulley diameter also. There are available pulley diameters in the chart also. Okay? So here is the list of available pulleys for the 3V combo or combination. Obviously the 3" is here. And so following our ratio, we can select 10.6 to get to the closest ratio. Now, the next step is to calculate the belt length. Yeah, I have it on the previous slide. Okay, calculate the belt length. The belt length is a simple ratio, 2 times the center to center distance, and this is in inch, plus okay? So it's a simple formula. It's just geometry. Now, based on this belt length, then we need to select the belt here. No. No. In this chart, okay? So here, 3B850. 85 is in inches and 850 is 85 inches. So you select the closest one. So based on this, 3B850. Okay, this 85 is the length. 3B is the belt family. Any questions so far? Okay. So that's the. Oh, sorry, this is 4. All right. So now we go to the 6th step. The 6th step, we calculate the belt capacity. And the formula goes as such. We have the base horsepower. I'll just write it here. Speed, ratio, adder, times the coefficient of our contact times the coefficient of belt length. And these are all looking up charts. Okay? Let's look this up in each one of the tables. The arc contact is looked up first with this parameter D minus D divided by C. So this is needed to look up the coefficient of arc contact. That's the closest one. We can interpolate if you want. So let's just pick 0.97. Okay? Coefficient of belt length is here, right next to the belt length. 1.06. Okay, everybody still with me on that catalog? You can look it up yourself. So this belt length also add to the capacity of the belt because you just have more mass. Yes.
Correction factors.
Belt. Sorry.
1.06. Yeah, it's the correction factor.
Yes.
That's the coefficient.
There's the coefficient of belt length. Yeah. Okay. So next up, we have the base capacity. So you find this on your catalog. I believe it's page table 7. Okay. So you have 3. Oh, it's here. So you have 3 horsepower and 900 RPM. So you arrive at this cell. That's the base horsepower. 1.34 horsepower per belt. So this is the base horsepower. These are just correction factor. But then we need to add the speed ratio adder, and we have the small sheave as 3, and the RPM is 900. Now, it does say for small sheave in inches, but I've always suspected, I wanted to ask Bendo for in many occasions. I have not done that. I believe it should be the speed ratio on the top, but I have not confirmed that. So 1.34 plus 0.2. Oh, wrong color. So 1.34 plus 0.2 got here, right? Small sheave 3, according to that, and 900 horsepower. But you know, I have my curiosity whether this is actually speed ratio. I have not confirmed that, so I don't know what to tell you. I'll contact them. But if these were speed ratio, then we will be here because we're at 3.6. Okay? It'll be 0.12, 21. Any questions on the capacity? This is the main capacity. Okay, this is the main base horsepower rating for a pulley size and the belt, the pulley ratio. Yes.
For this one, yeah, this one. Where did you get the 3 for?
Sorry. This is not the 3 horsepower. This is 3 inches.
Oh,
Sorry, my bad. Multitasking here. So 3 inches, small sheave diameter, and 900 RPM. Okay? So you see that the base horsepower is actually this one. And everything else is just a correction factor. Okay? This is the main number you're looking for on this table. And you see that for bigger pulley, what do you notice as the trend?
higher base horsepower.
Okay, does that make sense? You think? Why is the bigger pulley here results in higher horsepower capacity? Think about it. The belt wraps around the pulley, right? And what does smaller pulley means? It's faster, but you basically bend the belt much more. And do you think that's better or worse for the belt?
Worse.
It's worse, right? So bigger diameter gives you a better radius, and so the horsepower capacity is more. Okay? With smaller diameter, you're actually developing more heat and more damage to the belt. So smaller diameter is worse, bigger diameter is better, but then you'll run into space limitation many times. Okay? So there is also the RPM effect also. But RPM and horsepower kind of go hand in hand. Bigger RPM, obviously bigger horsepower. So now that is our main belt capacity calculation, which then results in 1.52 horsepower per belt. Now, what was our requirement? What was our horsepower requirement?
6.
So, we're going to go into a multiple belt situation. And so seventh step is number of belts. You cannot have a non-integer, obviously. So 6 horsepower needed divided by 1.52. So we have 4 belts. Okay? Of course, you have to have integer number of belts. And finally, if I want to know the safety factor, then it'll be, remember, conceptually, what is safety factor? What is the concept of safety factor? It's how much you can take divided by how much the actual load is, right? So if I can do, if this table can do 200 kilograms, but the specification is only 100 kilograms, then you have a safety margin of 2 times. So therefore, this is the number of belt 4 times the belt capacity divided by the design horsepower. Can somebody calculate this? What is 4 times 1.52?
6.08.
Is it? Okay. So we have just a slight margin here. Okay. Pretty much we just have enough. If you want more, then add 1 more belt. Now there might be situations where I specifically mentioned I only want 1 belt. What does that mean then? Then we're gonna have to go with a bigger pulley if allowed on the smaller diameter, or we just go with a bigger belt, right? If you look at, go ahead and look at the 5B charts. I don't have it here. Go ahead and flip to the Bendo Design Catalog. The 5B, compare the 3B tables and the 5B tables for the horsepower rating. What do you notice?
It's up from like 70.
So this is a 3BX. This is a 5B. Let's go 5B. Now, the 5B will require a bigger pulley because simply it's bigger, right? It's thicker, sorry. And so you notice that for 900 RPM, even with the smallest pulley, we're talking about 10 horsepower. So that easily fulfills this. But we're going to have to require the smaller diameter to be bigger. So that's if you want a single belt. But if you want a thin belt and a small pulley, then you're going to have to go with multiple belts. Okay? So you will see this situation in chain also. And many times when you are designing something, you have other surrounding factors, right? Like space. Like I don't want this big of a pulley. I just want a 3-inch pulley because then a big pulley will interfere with something else on the side. There is budget, of course. So there's many factors in real world design. But here's an example where we're just going to have to go with multiple belts of a small belt. Any questions? Yeah. Yeah.
you determine the 10.6 that
Well, first of all, the smallest pulley, we have to go with a 7.1 pulley. And then in this situation, we're 900 horsepower, right? Sorry, 900 RPM, 900 RPM. So this is the base horsepower for a 5 feet.
But yes, sir. Like what is 10.6 symbol?
That's the big diameter pulley.
Yeah, why is that? What's 10.6?
Speed ratio.
3.6.
Mhm.
It's versus 2. So speed higher than 6. The small diameter is 3. Then the ratio.
You want to reduce from 900 RPM to 250 RPM. So this is your speed ratio. Which will be the ratio of your pulley diameter?
Yeah, so you multiply that with 3 and that's
So 3 times 3.6 is approximately 10.6. That's the closest pulley you can get. So that list is a list of available pulley. Otherwise, you'll have to manufacture your own. You can always do that, but it's just more expensive. Does that make sense?
Wait, why can't we fly by 3? That's because the speed ratio is basically the same as the diameter.
So,
Ah.
right? So the big D is approximately, right? The small d times the speed ratio. So we have 3.0 multiplied by 3.6. What is it, 10.8? So the closest one, closest size is 10.6 inch. Okay? So that's the procedure to calculate the requirement for that. If there is no more questions, go ahead and do the post test.
Nggak masuk akal.
Ya nggak apa-apa, buat yang bikin aja. Nggak kayak yang tadi ya, yang tadi kan hasilnya berarti pas udah beres
Bisa itu nyampe.
jangan di express. Apa sih yang pengen doang? Ini bisa tuh yang
Nah, bener lah bilang expert itu